Hello everyone. In the last lectures, I derived condition for the gravitational instabilities using the very simple models. More accurately, we need to use the linear perturbation theories. We need to write the equations for the continuities, Euler equations, Poisson equations in a cylindrical coordinate. And also we need to combine with the equation of state to relate pressure and density. So I don't explain how to solve these equations, but I'd like to introduce how to solve these equations to find out the dispersion relations. At first, steady state, so round t equal to the 0. Then we introduce the perturbation. Delta rho over rho can be a function of the exponential I omega t plus kr. So this corresponds to the situation we consider the waves. Some regions become denser than other regions. By substituting these perturbations into the original equation, find out the relation between the omega and the k's. When the omega squares becomes positive quantities, it becomes stable. When the omega square is a negative quantity, this region becomes unstable. Because the omega square is negative quantities, then omega can be expressed plus minus I alphas. Alpha is a real number. Alpha is a positive quantities. Then exponential I omega t can be expressed exponential minus alpha t's or exponential alpha t. Exponential minus alpha t is a decreasing functions. So even if the perturbation exists, this perturbation is quickly decreasing. But exponential alpha t terms, in this case the magnitude is increasing with times exponentially. So this corresponds to the unstable mode. So magnitude increases with times. So if the omega square is a negative quantities, show the unstable mode. When we solve the linear perturbation theories, dispersion relation is given by this equation. Omega square equals c square times k minus pi g sigma over c square plus omega square minus pi g sigma over c squares. So this equation is very similar to the equation we derived before. Minimum value for the omega square is given by this. So if this minimum value becomes negative quantities, it's a condition for the gravitational instabilities. By changing this equation, you would find that this c omega over pi g sigma have to be just less than 1. So we introduce a new value of the Toomre Q parameters, defined c omega over pi g sigmas. By using the linear perturbation theories, we derive the Toomre Q parameters. But this is very similar, the equation. We derive the square root 6 c omega over pi g sigma is less than 1. Just only we have this difference of the factor of the square root 6. Except the square root 6, we have the same equation. Then gravitational instability in the dust layers. So we explained dust particles fall to the midplanes, forming dust-rich layers near the midplanes. Then we'd like to examine stability of such dust-rich layers. The condition for the instability is the Q value has to be less than 1. You can substitute C H omegas. The sigma over H is larger than the omega square pi g. So sigma can be expressed to H rho. Omega squares G m substance over R cube. Then this equation is rho is larger than the m substance over 2 pi r cubes. So this is nearly equal to the density of the stars can be expressed as m substance over divided 4 pi over 3 r cubes. So we distribute the mass of the stars. So this is a low substance. Gravitational instability is set when the local density of the gas becomes larger than the density calculated from the uniform distribution of the mass of the stars in that region. Then gravitational instability is set and the local density increases quickly. Gravitational instability of dust-rich layers form a number of planetesimals. So from the dispersion relations, omega square first becomes a negative quantity. At this point, this C is equal to the 0. So at this point, omega squares equal pi g sigma over C squares. So from this equation, C square equal pi squared g squared sigma squares over omega squares. In the case of C, the most unstable wave numbers can be calculated from this equation. By combining these two equations, you can substitute this C squares into this equation. Case of C is related to 2 pi over lambda sub c. Lambda sub c can be calculated 2 pi squares r cube sigma over m sub star. Then the most unstable mode, the width of the rings can be calculated. Lambda sub c is given by this equation. To estimate mass of the formed planetesimals can be calculated. The area is estimated pi lambda sub c square times surface density of the solid particles sigma d. If you use a Hayashi model, 7 gram square centimeters r over 1 AUs minus 2 over 3. And if you substitute these quantities, you will get 1.2 times 10 to 15 kilogram. Then from this mass, we can estimate the size of the planetesimal is about 3.2 kilometers, when the density of the material is 3 gram per cubic centimeters. 3.2 kilometer is very similar to the size of comet. So it is nice to find a mechanism to form planetesimals from small solid particles. But we still have a problem to be solved. So problem of this model. So from the Toomre Q values, we can estimate the scale height of the dust-rich layers. So dust-rich layers can be estimated is less than the 8.2 times 10 to minus 5 scale height of a gas. This is really thin layers. Then we can estimate the scale height of the dust layers if you consider the weak alpha of the 10 to minus 4. And the size of the solid particle is 1 meters. Then even in that case, the scale height becomes 3.2 times 10 to minus 3. This is much larger than the scale height of the. It's quite difficult for a particle to sink to form a dust-rich layer to induce the gravitational instabilities, because the conditions for the gravitational instabilities require the very thin dust layers. But if you increase surface density by a factor of 40, it might be possible to induce the gravitational instabilities. If you increase the surface density of the sigmas, this 8.2 times 10 to minus 5 is increasing to the about 3.2 times 10 to minus 3. But we need to increase the 40 times the surface density of solid particles. We consider such a mechanism, the Rossby wave instabilities. Rossby wave instabilities produce some long-lived anticyclones in a disk. Solid particles might be accumulated at the center of the anticyclones, increasing the density of a factor of 10. So we could find a mechanism to increase the surface density of the solid particles at the center of the anticyclones, but it's still difficult to increase the density of the solid particles by the factor of 40. The gravitational instability model was proposed to explain the formation of the large particles from the very small particles quickly in a disk. But still, we have a problem to be solved to accept the gravitational instability model as a reasonable model for the planetesimal formation. This is the end of the section for the gravitational instabilities and also the end of the chapter of the planetesimal formations.